Imagine a world where the very space around you could shrink, not as an illusion, but as a fundamental reality, simply because you are moving fast enough. It sounds like science fiction, but it is a cornerstone of how our universe truly operates, thanks to one of history's most brilliant minds. Today, we are exploring this mind-bending phenomenon. Special relativity explains length contraction as the observed shortening of an object in its direction of motion, relative to an observer who is not moving with that object. This effect is not a trick of perception or an optical illusion, but a real physical change in the measured length of the object, a direct consequence of the universe's fundamental speed limit, the speed of light. The core of this idea stems from Albert Einstein's two postulates for special relativity. First, the laws of physics are the same for all observers in uniform motion. Second, the speed of light in a vacuum is the same for all observers, regardless of their own motion or the motion of the light source. These two simple yet profound statements revolutionize our understanding of space and time. If the speed of light is always constant for everyone, and time itself can appear to slow down for moving objects, then space must also adjust to maintain this universal constant. An object's proper length is its length measured by an observer at rest relative to it. Any observer moving relative to that object will measure a shorter length. So, how do these rules make an object shrink? Think about it this way. If a light beam travels from one end of a moving object to the other, for a stationary observer, the light has to travel a longer path because the object itself is moving during the light's journey. But because the speed of light is constant for everyone, the only way for the stationary observer to measure the same speed for light, while also observing a longer path and a different passage of time, is for the length of the moving object to appear shorter in the direction of its motion. It is a necessary geometric adjustment within space-time. You will not notice length contraction in your daily life because it only becomes significant at speeds approaching the speed of light, also known as relativistic speeds. For example, a spacecraft traveling at 50% the speed of light would appear 73% of its original length to a stationary observer. This effect is symmetrical, meaning that if you were inside that spacecraft, you would observe a stationary planet as being contracted in the direction of your motion. It is a relative effect, depending entirely on the observer's frame of reference. The degree of contraction is dictated by the Lorentz factor, a mathematical expression that quantifies how much measurements of space and time are altered at high velocities. This incredible concept demonstrates that our intuitive understanding of an absolute and changing space is incomplete. Special relativity reveals that space and time are interwoven into a dynamic fabric, with measurements of length and duration being relative to an observer's motion. Understanding length contraction, alongside time dilation, offers a glimpse into the flexible and interconnected nature of our universe, where objects literally change their dimensions to uphold the fundamental principles governing cosmic travel.